All right, okay, so this is graph theory. Okay, so this is an English taught class. Okay, and this is about graph. Okay, so I believe that you all know graphs. Okay, in discrete mathematics. So graph is just like a set of nodes, and there are links between these nodes. Okay, so for this course, we're going to discuss some problems and properties and some algorithms related to graph. Okay. And also, I may mention some of its applications in in computer networks or in social networks. Okay, but basically, I'm going to say that this course will be like a math class. You're going to see lots of proofs. You're going to analyze algorithms. Okay, and you're going to solve some mathematical problem. Okay, in terms of graph theory. Right. So let me start with the grading policy. Okay. So there are two exams, okay? So each accounts for 25% of the final grade. And I know that most of you have taken my courses before, right? Like data structures. So for my previous courses, you can use the internet during the exam. But starting from this year, I'm going to change the policy, okay? Because nowadays you can use ChatGPT, like O1 or O3. So in order to make a good exam, uh, I have to make those problem sets slightly or somewhat difficult, so they don't get a very high score. But there's a drawback that is, if you can use ChatGPT, then I cannot have some very simple but important questions in the problem sets, right? But sometimes it's these basic problems that are really important, okay? But nowadays, if you use ChatGPT, I cannot have those problems in the exams. So starting from this year, the exams will still be open book. So you can still bring any textbook, any notes, but you cannot use the internet, right? So that's a big difference between this year and previous years, okay? And before every exam, there will be an assignment, okay? So we have two assignments. Okay, so the purpose of these assignments are to help you to understand the material and to let you to practice some of the problems that you may see in the exams, okay? And because, just I mentioned earlier, this will be like a math class, so the assignments will be like some problems related to proofs, or some math problems you need to solve, okay? Or some algorithm design problems. And we have one group presentation. So this presentation contributes 20% of the final grade, okay? So for this group presentation, you need to form groups, okay? And you have to choose a paper related to graph theory, okay, obviously. And for computer science, there are many, many different disciplines or many different fields that are related to graph. Okay, so I think it's quite easy to find a paper that is related to your own research and also related to graph theory, okay? So you have to find one such paper and present it in this course. Okay. And because we are still in this airdrop period, so the final list of the students are not determined yet. So after, I think, after the midterm exam, more details on this group presentation will be announced, okay? Like how many students per group, or how many time do you have for a presentation, okay? And finally, the remaining 10% is the course participation, Okay, that is asking and answering questions in this course. Okay, so that's the grading policy. Are there any questions? 有问题吗？最重要，我想最大的事情是，就考试不用ChatGPT，不能上网。OK， 当然你还是可以带任何笔记。That's a good question. Okay, so yeah, I trust you, so you can bring like an iPad or any kind of pads. Okay. You can use Chinese or English. No, you don't have to. Yeah. All right. Any other questions? All right. Okay, so because this is about graph theory, and as I mentioned earlier, we're going to write proofs. And in order to write proofs, you need to have a solid understanding of like the basic definitions or the foundations of graph theory. So today we're going to start with some of the basic definitions and properties about graphs. Okay. Okay. So I guess we're going to start with graph, okay? So what is a graph? Let me first show you a couple of examples, okay? So this is one graph, okay? And this is the other graph. So this is one graph and this is one graph, okay? So this is graph 1. And this is graph 2. Okay. So what is a graph really? Okay. So as I mentioned earlier, there are lots of applications of graph theory in computer science, like social networks or vehicle networks. So first of all, if you want to define graphs, you have to have this like circles or nodes or vertices. Okay. So in social networks, these nodes or these circles can be like just you and me, or some user accounts or social network accounts. And for vehicle networks, these circles can be like cars. Okay. And for the internet, this can be like web pages. Okay. And so we need to have first to have a set of objects, okay? Objects that we are interested in, okay? So we need to first have a set of objects, okay? So after we have the set of objects, we then need to find like the relationship between objects, okay? So for social networks, this can be like friendship, okay? Or for the internet, this can be a hyperlink between different web pages, okay? So you have, I say, a set of relationships between objects. So basically, to define a graph, you have two sets, okay? First, the objects, and second, the relationships. Okay. So in graph theory terminology, we call these objects vertices, okay, or nodes, okay? Okay. So these two terms can be used interchangeably, okay? And for these relationships, we're going to call them edges or links. Okay. So what is an edge, or what is a link? It is just a pair of objects. Okay. So this is just a pair of objects, or we know that we should call them vertices. Okay. Okay. So let me give you another example. Okay, so this is one graph, okay? So we have to first define the vertex set, okay? That is the set of objects. So usually we're going to denote this set of objects capital V, okay? Okay, so this V is the vertex set. So this is the set of objects, and then we have the set of relationships, or the set of edges. Okay. So usually we're going to call this set capital E. Okay. And since edges are just pairs of vertices, so we can write down these edges as AC, AB, CB, and CD. I still missed one. So which one is missed? Yeah, BD, okay. Okay. Okay, so this is the edge set, okay? So far very boring, okay? The two sets, vertex set and edge set. But now we can start to talk about some basic properties, I'll say, about graphs. Okay, so first of all, here we have two graphs, graph 1 and graph 2. There's a big difference between these two graphs. So can you spot any differences between these two graphs? Connected or disconnected, okay? So for graph 1, it's like it is connected, okay? We haven't defined what is a connected graph, okay, but we're going to define it later. But for graph 2, it seems like it is not connected because we have a triangle and we have an edge here. Somehow they cannot be connect to each other, right? So intuitively, this is a disconnected graph, and this is a connected graph, okay? Okay, so I want to stress again that this is one graph, okay? This is not two graphs. This is just one graph. However, this one is not connected, okay? All right, so now we have to write down the definition of a connected graph. Okay, so, or you can say that, okay, suppose I want to write a computer algorithm or computer program, given a graph, possibly like this one, how to check whether this graph is connected or not. So this will be like a computing problem, but from the math side, you can also try to define what is a connected graph. So perhaps let's start with definition, okay? So what is the definition of a connected graph? Right? We all have the intuition, okay? So this one not connected, this one connected. But how to give the proper definition so that according to your definition, this one is connected, this one is not.
All nodes are connected by edge.
So what do you mean by all nodes are connected by edges?
Like, there's no disconnect between any two. Like, every node has an edge to another node.
Right, so, but for this one, every node has an edge
Yes.
connected to some vertex in the graph.
But it doesn't have edge connected to all its names. It's like that one doesn't connect to the other one.
Yeah, but for this one, it is not connected to this one by just one edge.
Yeah.
Right. So according to your definition, this one will be treated as a discrete graph. Right. So yeah, close, but not a perfect definition. We need some adjustment. Yeah.
Each vertex has a path to other vertex.
Each vertex has a path to another vertex. So first of all, a small adjustment, that is, for every vertex in the graph, it has a path to every other vertex in the graph, okay? But then you have to define what is a path. So you mentioned path, right? Yeah, so what is a path? So in order to use your definition, you have to first tell me what is a path, right? So what is a path? Well, so first of all, I think we all agree that for this one, so this is a path, okay? And for this one, this is not a path, at least for this graph, okay? Because this edge does not exist in this graph, okay? So this one is not a path for graph 2. But for this yellow path, it is a path, a valid path for graph 1. So to define the path for a graph, it is just a sequence of vertices, such that for every consecutive vertices, there's really an edge between them, okay? So a path, let's call VK, okay? So to have a path, you would need to have a sequence of vertices, okay? Okay. So the Heidegger idea is that for every pair of consecutive verses in the sequence, they are adjacent. Also, by adjacent, I mean there's an edge between these two verses. Okay. So sometimes I'm going to say U and V are adjacent. So this means there's an edge between U and V in the graph, okay? So sometimes I may also say U is incident to some edge UV, okay? So these two are very similar, okay? So when I want to stress that these two nodes, they are like neighbors or friends, I'll use this word adjacent, okay? But when I'm discussing about a vertex and an edge, such that this edge is like connected or attached to the vertex, then I'm going to use incident, okay? So some vertex is incident to like this edge, okay? Okay. And one notation I forgot to mention is, given the vertex set V and the edge set E, we often write a graph as this pair of vertex set and edge set. So whenever you see like this form G equals VE, this means this graph G has a vertex set V and an edge set E, okay? Okay, so now we have the definition of a path. Then the definition of a kinetic graph is straightforward, okay? So, a graph. So now we can use this notation, okay? So this means we have a graph whose vertex set is V and whose edge set is E. So we can say that it is connected if for any vertex in the graph, okay? So here I write V instead of G because V is really an element of this vertex set instead of the graph G. So G is just two sets, okay? But V, the vertex, belongs to the vertex set, okay? So there's a path between V and other vertices in the graph. Okay? So that's our definition for kinetic graph. So according to our definition, this one is not connected because for this vertex, there's no path connecting this vertex to this one or this one or this one. Okay? So this one is not connected. So if a graph is not connected, we call it disconnected. Okay, so any questions? All right, so this is like the math definition, okay? We can also discuss about the algorithm, okay? So given a graph, how to check whether this graph is connected or not. This is quite simple, yeah. So you can just traverse the algorithm using like a DFS or BFS to see whether you have visited all the vertices in the graph, okay? So if some vertices is not visited in your traversal, this means the graph is not connected, okay? So, yeah. Okay, so the next basic definitions I'm going to mention is components, okay? All right, so I haven't given you the definition of a component, but if I just ask you, okay, so how many components are there in this graph, and how many components are there in this graph? So we have two graphs, okay? So what is the number of components in each graph? I'll say an intuitive answer would be, for this one we have one component, and for this one we have two components, okay? So one component here and two components here. Okay, so what is a proper definition for components? So what is a component in a graph? So that according to your definition, we have one component here and two components here. Any suggestions? Yeah.
The number of connected graph in this graph.
All right, that's a good start. Okay, so well, I guess you try to answer the what is the number of components. So your suggestion is that the number of components is the number of connected subgraphs in the graph. Okay, so yeah, okay, so let's try this one. Okay. So in other words, this means what is a component? Well, a component will be a connected subgraph. Right, okay, so yeah, let's try this one. All right, so this is our first definition, okay? So we all know the meaning of connected. So what is a subgraph? So a subgraph of a graph is just like a smaller or like a subset of the original graph, okay? So recall that we have two sets, the vertex set and the edge set, okay? So if we take the subset of edge sets, then we get a smaller sets, okay? And we can use those smaller sets to build a smaller graph, okay? So perhaps this one. So this is one graph, okay? So what is a subgraph? So this will be a subgraph, okay? Now, let's try to apply this definition to our previous examples. Okay, so for this graph, recall that a reasonable answer to the question of the number of components in the graph, a reasonable answer would be 2, okay? So we have one component here and one component here, so this makes 2, okay? So if we try to apply this definition to the graph, okay, so let's count how many connected subgraphs are there in this graph. Then you're going to see that actually there are more than 2 connected subgraphs. Okay, so for example, you can so these 2 vertices and this edge, they will form a connected subgraph of this original graph. Okay, so similarly, if I take these 2 edges, again, they will form a connected subgraph, okay? So based on this definition, the number of subgraphs or the number of components will be greater than 2, okay, instead of 2. So we need to, again, adjust this definition a little bit. So we're not looking for all connected subgraphs. We want to find some spatial connected subgraphs. So we need to add some like constraints or properties. Maximum, okay? Right? All right, so what is a maximum connected graph? So can you elaborate on this maximum? Yeah, so what is a maximum connected subgraph?
The most number of vertices.
Okay, so you want to have the most number of vertices in a subgraph,
Yeah,
all right?
and it's
And
connected.
it's connected, right. So in this graph, so what is a maximum connected subgraph? So according to your answer, it will be the one that has the most vertices. So the answer will be under this one. Right, because for this one, this only has 2, so this one has 3, so this one wins. So we're not looking for maximum. This is like too restrict. Okay, so we want to have a maximum. Okay, so now, so what is maximum? Local maximum. This means you cannot really add any more vertices to this subgraph. Okay. Okay, so this maximum means, well, according to his words, this is local maximum. And what is local maximum? This means you cannot add any more vertex to it and still make the component connected. Okay, so let me give you an example that is not maximal kinetic graph. So if we consider this one, okay? So actually for this one, you can still add this vertex and this edge to make it connected, okay? So this one is not locally maximum, okay? But for this one, it is locally maximum because you cannot add any more vertices and edges and still make it connected, okay? So this one is local maximum. So I should add any more vertices and edges, okay? All right, so this is the components, okay? Okay, so next, degrees. I guess you all know this. Okay. Okay, so the degree of a vertex is just the number of neighbors or the number of edges incident to a vertex. So for vertex, so for vertex 2, so this d of v is just the degree of v. So for this graph, it is 3, okay, because it has 3 neighbors, so 1, 3, and 4. So if we consider vertex 5, then the degree will be 1, okay. Oh, sorry, so I should change, okay. So the degree of a vertex is the number of okay. So to find out the degrees, you just count the number of neighbors or the number of edges incident to the vertex. Okay, so that's degrees. All right, so for degrees, we can have some simple properties. Okay. The first one relates the total degree. Okay. To the number of edges. Okay, so in this course, we're going to use n to denote the number of vertices, that is the size of the vertex set. And we're going to use m to denote the number of edges. Okay. So yeah, so the number of edges is just m. Okay. So is this equation correct? No. Okay. So how to modify it so that the equation holds? So what is the relationship between the number of edges and the total degree? Okay, so let's consider this example. Okay, so there are 5 edges. Okay, and what is the total degree? So the total degree will be 2 plus 2 plus 2. That's 6. And sorry, there are just 4 edges. Okay, 4 edges, and so far we have 6 degrees here, and then we have 2 degrees here. So 8. The total degree will be 8, and we have 4 edges. Okay. So at least from this example, we can see that the total degree will be twice the number of edges. Okay, and you can try this one. Okay, so the total degree will be 2 plus 3 plus 3 plus 2. It will be 10. Okay, and we have 5 edges. Okay, so again, the total degree is twice the number of edges. Okay, so this one is quite simple. So do you have a proof for this example? Sorry? Do you have a proof for this equation? there's a very simple proof, okay? So I'll say there are two different ways of computing this total degree, okay? So the first way is to just consider all the vertices in a graph and just sum up their degrees, okay? This will be like the standard way to do so, okay? Just consider all the vertices in a graph and compute the sum of their degrees, okay? So this is just like what I did earlier, okay? So I compute the degree here, so this 2 plus 2 plus 2 plus 1 plus 1, okay? So this is like the first way of computing the total degree, okay? And the second way of doing so is that I consider every edge, okay? So now I consider this edge. So I know that for this edge, it contributes 2 degrees to the total degrees. So one for this endpoint, another one for this endpoint. Okay, similarly for this edge, it contributes 2 degrees to the total degrees. So for each edge, it contributes 2 degrees. Okay, so then I can just count the number of edges, okay, and multiply 2. So yeah, so every edge contributes 2 degrees. So this is why the equation holds. Okay. So we have 2 different ways of computing the same numbers. So these 2 numbers must be the same, okay? Okay, and also as a simple consequence of this equation, we know that the total degree must be an even number, right? Because it is 2 times some integers. Okay, so this n must be an integer. So the total degree must be an even number. So if you have say you have a sequence of degrees for some graph, okay? And if you find out that the total degree is not even, then you know that something's wrong for the degree sequence. Okay. The next property is about the minimum degree. So what is the minimum degree of a graph? So it is just you consider all the vertex degrees and pick the smallest one, okay? So that is the smallest degree or the minimum degree. So for this graph, the minimum degree will be 2, okay? And for this graph, the minimum degree will be 1, okay? So just find out the vertex that has the fewest neighbors or the fewest instant edges. Okay, so the second property is that if the minimum degree, recall that we use n to denote the number of edges, the number of vertices. So here, the statement is that if the minimum degree is at least n minus 1, okay? So recall that this n is the number of nodes. And then the graph is connected. Okay. So is this statement correct? So say n is 4, okay? So this means you have 4 vertices, okay? Okay. So 4 vertices in a graph, And we also have the assumption that the minimum degrees is at least m minus 1, which is 3. Okay? So this means for this graph, every vertex has at least 3 neighbors. So is the graph connected? So let's try. Okay, so everyone should have at least 3 neighbors. And by the way, for this course, we do not have so we do not have this type of edges. Okay. Okay, so for this type of edges, these edges are between the same 2 vertices. Okay, so for these 2 vertices, there are multiple edges between them. So we do not have this type of edges in our graph or in this master. Okay, so this is called parallel edges. Okay, or multi-edge. Okay. So in other words, for this course, for every 2 vertices you choose, there can be at most 1 edge between them. Okay. You cannot have 2 or even 3 or 4 edges between the same pair of vertices. And edges like this are called self-loops, okay, because it only has 1 endpoint, okay? So the edge goes back to the original endpoint, okay? So we do not have these self-loops, okay? Okay, so based on these 2 assumptions, if every vertex has at least 3 neighbors, then the graph, or at least this top left vertex, must have these 3 vertices as its neighbors. Okay. Similarly, for this one, it has the remaining 3 vertices as its neighbors. Okay. So it turns out that this graph is not only connected; it is like a complete graph. By complete, I mean for every 2 vertex. For every 2 vertices you choose, okay, there's always an edge between them, okay? So this is called complete graph. So we will use this Kn to denote a complete graph of m vertices. So, and again, what is a complete graph? It is a graph where for every 2 vertices, there's an edge between these 2 vertices. Okay. So for any 2 vertices u and v in the graph, there's an edge between them in the graph. Okay. So that's the definition of a complete graph. Okay. So if you have this kind of properties, then you actually have a complete graph. And if you have a complete graph, then certainly the graph will be connected. Okay. So the proof will be yes, because the graph will be complete. Will be a complete graph. Okay. All right. So let's take a break. Okay. 就只要教室空间够就可以。
那我们是拿加签单。
对，就是你就候补应该就会有那个加签单。对。
我们要签这个是我要那个硕士底面的那个课程，然后它的课程代码有2个，所以我们要拿硕士的那个课来给你签，对不对？
我的建议是你去问系办，会比较，因为他们会比我更清楚。我搞不好跟你讲错了，对。这个我是不是去那个？对，应该是无法列印系统加印，对。所以你有办法到系统印加签单吗？
因为那个选课系统上面是以额满的，我就不能再选进来。
可是应该可以候补嘛，我记得。
就是它以额满的话就不能候补了。
哦，是啊。
还是可以啊，我不知道。
候补的意思不是就是让你候补嘛？
我有选。
这样不是在候补。
对啊。可是我没有在里面，就我那课是直接不见。
我的认知应该是可以的啊，但是我一定会让你签。就是说，我觉得就是 follow 这个规定，你如果不是很确定，你去问一下系办。对，对，OK。对，就是如果你要加签的话，就是把那个到系统印加签单出来。对。 All right, so let's continue, okay? For this statement, we consider like the minimum degree. And given the minimum degree, can we guarantee the graph will be always connected, okay? So if we consider degree, so a vertex degree is just the number of neighbors for a vertex. So the maximum degree you can have for a graph that has m vertices will be m minus 1, okay? So say you have 4 vertices in a graph, then the maximum degree will be 3, okay? Because you cannot be adjacent to yourself, because we earlier mentioned that we do not have self loops. So really the maximum degree you can have, the maximum possible degree you can have is m minus 1. So this statement says that if the smallest degree is like the maximum possible degree, then the graph will be connected, okay? This is not very surprising because this means that the graph is very dense in the sense that, well, there are lots of edges in the graph. So naturally, the graph will be connected, okay? So next we're going to like lower this value, okay? So we want to have a smaller minimum degree, okay? So not everyone is connected to all the other vertices, okay? Perhaps you have some pair of vertices that are not adjacent, okay? So we're going to try. So the value here is n minus 1, okay? We're going to consider half of it. So we're going to consider n minus 1 divided by 2, okay? So the statement is very similar to the previous one. The only difference is here the threshold. Instead of n minus 1, now it becomes n minus 1 over 2. So is this one correct? Again, you can try some examples. Okay, so for n, let's try again, n equals 4. So n minus 1 over 2 will be 1.5. Okay, so this statement, the assumption of this statement is that for every vertex in the graph, it has at least 1.5 neighbors. Because the number of neighbors must be an integer, so this means every vertex has at least 2 neighbors. Okay, so you have 4 vertices, and everyone has at least 2 neighbors. Can you guarantee that the graph must be connected? So yeah, so you have to, for every vertex, you have to add 2 edges. So can you make a disconnected graph?所以大家想的是，在这个4个点的 graph 里面，你能不能在每一个点都加2个边，然后让这个 graph 是不是连起来的？Okay, someone is nodding, so you think it's possible? So how? So it must be connected. Yes. So why?
我刚举到7，因为那个如果你把它拆成2个一半的完全子图的话
So what do you mean by 完全指图？我真的不知道。
完全的 complete graph
哦，OK。
的话，你的边数刚好会是一半一半，
啊哈。
就是会加起来会那个
啊哈。
1/2个点跟2/2个点跟2/2个点，然后的完全子，
啊哈。
这是最糟情况。
为什么这是最糟的情况？所以最糟情况是什么意思？你的问题是？
我们有4个点嘛，
对。
然后每个点都是2个 degree 的话，加起来就是8 some degree， 然后就用刚那个定理，你会发现说你最多就4个边，你一定要有4个边才会成立。
Well, okay, so let me first write down your proof, okay? So because the minimum degree is m minus 1 divided by 2, so the number of edges, the total degree is at least 4 times 2, which is 8. So this implies the number of edges is 4. Okay, good. So if you have 4 edges in a graph that has only 4 vertices, then the graph must be connected. Okay. So you can try this. Okay. So no matter how you put these 4 edges, the graph must be connected. Okay. Okay, excellent. Okay, I haven't thought about this proof before. Okay, so but can we generalize this proof to more vertices? Okay, let's try. Okay, so okay, so the total degree is at least n times n minus 1 divided by 2. Okay. So now we have another question. Okay, so if you have we have m vertex. So what is the number of edges you need to guarantee the connectedness of the graph? That is, say for this example, if you tell me that we have 4 edges, then no matter how you place these 4 edges in the graph, it must be connected. Okay, so now we have to have a similar argument, but for more vertices. Okay, so instead of 4, we have to consider m vertices. So if we have m vertices, what is the smallest number of edges you need to guarantee the connectedness of, or the connectivity of the graph? So let me first give you some examples, okay? Let's try 10, right? So if we have a 10 vertex graph with 20 edges, okay? That's all the information you have for this graph, okay? So clearly there are many different ways of drawing this kind of graphs, okay? 10 vertices and 20 edges, okay? Can you guarantee that no matter how you draw the graph, it must be connected? 所以现在你有10个点，我要你画10个点跟20个边，你有没有办法说，哎，不管你这20个边怎么画，你画出来的图一定会是连起来的，有可能吗？ 哎，之所以要讨论这个，是因为我们想要把刚刚那个同学的这个 proof， 看能不能延伸到更多点的 case，OK？、Any thought? Yeah, so why?
Because it could still be disconnected with separate components.
Right, so how to compute or how to generate this type of components?
I think if you wanted to complete, you need 9 edges. Because I think it's n minus 1. You need n minus 1 edge.
But it is more than n minus 1 here.
Yeah, so it's not guaranteed. Right?
If you only have n minus 1 edges, then clearly, I'll say it's very easy to construct a graph that is not connected. But for this example, 20 is way more than 9. So perhaps it is possible to guarantee the connectivity. Yeah. But you mentioned that it is possible to create a disconnected graph under these two assumptions, right? So how to create such a disconnected graph?
The vertex, you can make 2 separate components.
Right.
Yeah.
So what is the size for these two components? Or the number of vertices in these two components?
You can draw 6 and 4.
6 and 4? Okay, so how to put these 20 edges to these two components? Okay, so let's try. Okay, so 1, 2, 3, 4, 5, 6. 6 here. So still 14. Okay.
Or you could put 15, I think. 15 on the 6.
All right. So far we have 13 here and 6 here. We need one more. Okay, so
Add 15 to the left, and then 5 on the right side. And then there's 2 more on the, you have 2 more on the left side.
so how to put 2 more edges?
Top left,
Top left. Oh, right, this one. Okay.
and the bottom, the left and the bottom right can still be connected.
Yeah, that's okay because we only have 20. Okay. Yeah. So this would be a counterexample. Okay. So in this example, we have 10 vertices and 20 edges. Still, you can generate disconnected graphs. Okay. So now how about 30? So now if you have, you can put 10 more edges to the graph. It seems like, no.
Just put the most extreme cases. For example, like 9, 1.
Exactly. So
it's a times 9. 7加1.
divided by 2. So here we have a complete graph of 9 vertices and 1 vertex here. All right? So what is the number of edges here? If you have 9 vertices and it is complete graph, divided by 2. Right, okay. So there will be 36, okay? So if you have 37 edges, then you must have a connected graph. So what is, how to get this number here? So this is the number of edges in a k m minus 1 plus 1. Okay. So if you have this many edges, then no matter how you draw the graph, it must be connected. Okay. So what is this? This is just m minus 1 times m minus 2 divided by 2. Okay. Okay, so I think another way to put this is so I guess I'll leave the proof for this statement as an assignment. Okay. Yeah, because we haven't really proved it. Okay, what we just show is that if we only have this many vertices, or sorry, this many edges, then we can still have a disconnected graph. Okay. So now we guess that if we have this many plus 1, then it is impossible to find a disconnected graph. Okay? So actually we haven't proved it. Okay? So perhaps it will be wrong, perhaps. Okay? But anyway, this will be in your first assignment. Okay? And yeah, suppose this is true. Okay? Now let's back to his proof. Okay? So now we have the total degree is at this number, which means number of edges is at least this number. Okay? So recall that we try to prove this one. Okay? So every vertex has a minimum degree. Oh, sorry. Every vertex has at least m minus 1 divided by 2 neighbors, and want to show that the graph must be connected. Okay, so the idea of our previous proof is that now, since we have the minimum degree, and we can have the minimum total degree. Okay, so we just compute the n times the minimum degree. That will be the smallest possible minimum degree. Okay, and since we have the relationship between total degree and number of edges, we know that this number divided by another 2, we get the smallest possible number of edges. So it tells us that the minimum number of edges we have is this number. Okay? But this number can be less than this one, right? Because here the denominator is just 2, but here is 4. Okay? So since this denominator is greater, which means this one can be smaller than this one. Okay? So if you consider this example, okay? So this will be, let's try this example, okay? We know that we must have at least we must have at least 37 edges to guarantee the connectivity of a graph, okay? So now if we only know the minimum degree is 9 divided by 2, okay? This is our assumption tells us, okay? Our assumption says that the smallest degree is n minus 1, because n here is 10, n minus 1 becomes 9, so 9 over 2. So this is the minimum degree times 10. So this is 45. So this is the minimum degree, minimum total degree. Okay, so since this is the minimum total degree, this tells us that the number of edges is at least 22.5 edges. Okay, so under the assumption that the minimum degree is at least n minus 1 divided by 2, we can conclude that we have at least this many edges. But if we only have this many edges, we cannot guarantee to have a connected graph. In other words, we cannot extend your idea to graphs with more vertices. OK， 所以刚刚的同学的 idea 是从 minimum degree 出发，然后去看 total degree， 我们就知道 total degree 至少会是多少。然后知道 total degree 至少是多少之后，我们就可以用刚刚这个关系，所以你知道 total degree 除以2就会是 edge。OK， 所以我们有 minimum degree 是刚刚的假设是 n 减1除以2，所以就是这个，所以 total degree 至少就会是45，所以 total degree 如果至少是45，就代表我们至少会有 22.5 个 edge。可如果我们只有 22.5 个 edge， 还是有可能会有 disconnected graph。OK， 所以就像刚刚这个，假设你这边有一个 K9。OK， 那这边是1，事实上这个就已经是有36个 edge， 你即使画了36个 edge， 都有可能会 disconnected， 更何况是你只有 22.5个 edge。OK， 所以刚刚那个 idea 就没办法 extend 到更多的 vertex。OK，but anyway, it's I'll say cute proof for at least the case where n is equal to 4. Okay, so good. All right, so this approach fails. Okay, so we need another proof.
刚说要把它分成2半是最好。
Yeah, so but you.
因为你说至少要是2分之 n 减1，最少的那个 degree 每一个点。
啊哈。
所
设我们它是不连通的话，那我们要让每一个点至少要是2分之 n 减1的话，我们至少要两半都是2分之 n。如果我是不连通的，我一边是2分之 n 加1，一边是2分之 n 减1的话，我这个条件就绝对达不到。
All right. Okay. So let me try to formalize your idea. Okay. First of all, you mentioned that you assume that there are two components, right? So this implies that you want to prove it by contradiction. So we assume that even if you have this n minus 1 divided by 2 minimum degree, you may still have disconnected graph, okay? So we're going to prove it by contradiction, okay? So for the sake of contradiction, so assume the graph has at least two components. Let's call them C1 and C2, okay? So we have a component C1 here and another component C2, okay? So now for every component, so for example, C1, we can find a vertex U, and for C2, we can also find a vertex, because a component must have at least one vertex, okay? So we can always find at least a vertex in each of these two components. And now we know that the minimum degree of these two vertices, U and V, they're at least n minus 1 divided by 2, okay? So they have lots of neighbors here. Similarly, for vertex V, it has n minus 1 over 2 neighbors, okay? So see, how the way I draw these two graphs is that these two components, okay? You see that all the neighbors of U, they are in this component C1, and all the neighbors of V are in C2. Is it possible that some of V's neighbor is in C1? So C1 is a component, C2 is also a component, okay? There are two different components. Suppose I fix a vertex V in the C2, and I try to find all the neighbors of V. Is it possible that V has some neighbors in C1? So why not? So what happens if there's a vertex here which is adjacent to V? Right, so V cannot have any neighbors in C1. Otherwise, these two components will be like, they will be merged into one larger component, okay? But recall what is the definition of a component. It is a maximal connected subgraph, okay? So if you have an edge here, then these two can no longer be a component, okay? So all the neighbors of V must be within this C2. Similarly, for every U's neighbors, they must be in C1, okay? All right, so the idea of proof by contradiction is try to find some contradiction, right? So you have this, you assume that the statement you try to prove is wrong, and you try to find some weird thing, weird property, okay? Or in fact, contradiction, okay? So where's the contradiction? And recall that n is the number of vertices in the whole graph, okay? So can you see where's the contradiction? Yeah, so where's the contradiction?
然后把它通分的时候变2分之 n 减2，然后它会小于2分之 n 减1，所以它应该再加一个。
I think there's a simpler contradiction in this graph. All right, so let's count, okay? So what is the size of this component, C1? So how many vertices are there in C1? And similarly, how many vertices are there in C2? So now let's C1 has this vertex U, okay? And U has m minus 1 over 2 neighbors. And all these neighbors are in C1. Now we know that C1 has at least 1 plus the number of neighbors for U. Similarly, C2 has this many nodes, okay, or vertices. So, where is the contradiction? So, how many vertices are there in the whole graph? So if you just compute the sum, so the graph has at least this many vertices. So what is this number? So this number is m plus 1, okay? So that's the contradiction because we know that the whole graph has exactly n vertices. But now you said that the graph has at least this many m plus 1 vertices. So that's a contradiction, okay? Okay. So that's the proof, okay? Okay, so so the answer is yes, okay? So if the minimum degree is m minus 1 divided by 2, then the graph must be connected, okay? But if you consider these two proofs, okay, so first of all, in the first statement, we consider the case where the minimum degree is m minus 1, okay? Really, the proof is that for every 2 vertices, we can prove actually that they are adjacent, okay? So the graph is actually a complete graph. But for this one, because we use proof by contradiction, so we actually do not know like the structure of the graph, okay? So next I'm going to give you the second proof, okay? The second correct proof, okay? And in this second proof, you're going to see some of the structural property of this kind of graphs. Okay, so this will be our third approach. Okay. So the high-level idea behind this third approach is that in this kind of proof, in this kind of graphs, where the minimum degree is m minus 1 over 2, there's a very nice property about it, okay? So perhaps let me state the claim, okay? So if the minimum degree is at least m minus 1 divided by 2, okay? All right, so the claim says, so if you pick any two verses, and if these two verses are not friends, in other words, they are not adjacent or there's no edge between them, okay? So non-adjacent, okay? Which means there's no edge between them, okay? And actually I can prove that they have a common neighbor or they have a common friend, okay? So a common friend is like this, okay? So you have U and V, and they do not have an edge between them, but they have a common neighbor. Call it X, okay? Such that both verses U and V are adjacent to X, okay? All right, so if you have this claim, then almost automatically you have the previous claim. That is, the graph must be connected because the statement says, or the claim says, for any two verses, either they are adjacent, okay? And in this case, you have the path, right? Because to prove a graph being connected, you have to construct the path for every two vertices, okay? So one possible way is like the complete graph, where you have an edge for any two vertices, okay? So that's nice. But sometimes these two vertices, they may not be adjacent, okay? So in this case, the claim says, well, at least you can have a common neighbor, okay? So U can be adjacent to X, which is adjacent to V. So in this way, you can also construct a path, okay? So now for every two vertices you choose, there will be a path, which implies the graph is connected, okay? Okay, so OK， 所以前面这边第一个这个，我们在看 n 减1这个 proof 的时候，我们有说它事实上这个 graph 是 complete graph，OK，、所以任两个点，它们中间都会有一个 edge。既然两个点都有 edge， 那它们之间就一定会有 path，OK，、所以这是有点像是我们第一个 proof。那等一下我们会做的事情是，我们会去看说，如果你的 minimum degree 是至少是 n 减1除以2的话，那就算这两个点它们没有直接相邻，就像 complete graph 这样，它们可能不像 complete graph 那么好 ，OK， 那么可能中间有一些 edge 不见，但即使是这样，你一定都可以找到另外一个 vertex， 这个 vertex 它们是同时连到这两个你选到的 vertex U 跟 V。那如果有这样的 vertex， 你事实上就有一个 path，OK，、所以那就可以证明说这 graph 会是 connected 的。所以我们接下来要做的事情就是要去看说，为什么随便你选的两个点，只要它们没有相邻，它就一定会有一个共同的邻居。OK，right，、有问题吗？Questions? Okay, so let's try to prove the claim, okay? So now you have two vertices, okay? And they are not adjacent. And somehow you need to prove that they have a common neighbor. So, any idea?
Because there are n vertices.
Right.
And you minus u and v, so you have n minus 2 vertices. You divide by 2. So there are n minus 2 divided by 2.
Mm-hmm.
And the claim is n minus 1 divided by 2. So it's greater than n minus 2 divided by 2. That means u and v, if you don't look at those two vertices, and you put the other vertices, which is n minus 2 vertices, in the group, and you divided it, no matter which way you choose, there must be one, at least one vertex that it's selected by u and v.
Mm-hmm.
Yes, you know what I'm saying?
Yeah. Excellent. Okay. So let's try to formalize your idea. Okay. So you have a vertex u and vertex v. So you have m minus 2 vertices other than u and v. Okay. So u is adjacent to at least m minus 1 divided by 2 vertices here. Okay. And similarly, v is adjacent to m minus 1 divided by 2 versus in the set. Okay. So since this set only has m minus 2 vertices, then these two sets, they must have some overlaps. And this overlap means they have a common neighbor. Okay. Perhaps another way to prove this is again using proof by contradiction. Okay. So let's assume that they do not have common neighbors. Okay. So this means these two sets, they are disjoint. Okay. So if these two sets are disjoint, then this means, let's call this set S. Okay. So what is S? So S is just the original vertex set excluding U and V. So the size of S will be n minus 2. Okay. And usually we're going to use n of u and n of v to denote the set of u's neighbors. Okay. So both of these two sets, they are subsets of S. Okay. And so because we want to prove it by contradiction, we're going to assume that these two sets are disjoint. In other words, their intersection will be an empty set. Okay? Which means the size of S is at least the size of n of u plus the size of n of v. That is the number of neighbors of u plus the number of neighbors of v. Okay? So basically just this graph. Okay? So you can see that so this So this is n of u. And this set is n of v. Okay, and they are disjoint. Okay. So if they are not disjoint, then this inequality may be wrong. Okay. All right. Okay. But now we know that the size or the number of used neighbors is at least m minus 1 divided by 2. So this is at least this. Okay. Okay, so from this inequality, we get that the size of S is at least m minus 1. However, in the beginning, from the definition of this set S, we know that the size of S is exactly m minus 2. Okay, so m minus 2 is not greater than m minus 1, so that's a contradiction. Okay. Okay, so yeah, this shows that if the minimum degree is large enough, by large enough I mean m minus 1 divided by 2, then for any two vertices, if they are not adjacent, then we can always find a common neighbor between them. Okay. Right, okay. So any questions? 有问题吗？我们刚刚做的事情就是去看，如果这个 minimum degree 是这么大的话，我们事实上可以去说，这两个点它至少会有一个共同的邻居。那我们的 idea 就是用反证法 ，OK？ 所以我们会先找出那些不是在 U 也不是在 V 的点，就是这个 set S。所以所有的 U 的邻居都会在这边，然后所有的 V 的邻居也都会在这边。OK，maybe 我可以有一个问题给大家看，大家能不能知道为什么？就我们刚刚这边有一个假设，就是这两个 vertex 是没有相邻的。OK， 在这一页里面，我们哪里用到刚刚那个假设？我们有用到假设，就是他们没有共同的邻居，但是我们似乎没有用到 U 跟 V 没有相邻。但事实上我们会需要，所以在哪里？我们在哪一步隐含了我们使用到这个假设？可以再更清楚一点吗？
因为我们已经在找他们，就找他们两个点以外的点，所以我们已经先假设他们不相邻。不然的话，为什么要找其他点？
不，我们先找出这个 S 嘛，这个 S 的定义就是不是 U 也不是 V 的嘛。
那就是 n 那个2n减1啊，因为我们里面找外面的2n减1个点，所以我们已经假设 U 已经和 V 以外的2n减1个点有联系，所以它不会再跟 V 有联系。因为你有2n减2个点在外面，那你已经假设2n减1个点在 n减2个点里面，所以就不会跟 V 相连。
对，没错，所以就关键，如果是视觉上的话，就我们刚刚隐含用到了刚刚那个 U 跟 V 没有相邻的假设是用在这里，就是我们这边我们先把 U 所有的邻居都画出来，就是这个 N of U，OK？、那你会看到我们刚刚把这个 N of U 全部都画在这个 S 里面 ，OK？ 我们所有的 U 的邻居都会在 S 里面，那为什么？如果你不讲的话，事实上 U 也可能跟 V 是相邻 ，OK？ 但是前面的假设就已经告诉我们 U 跟 V 是不相邻，所以我就可以很放心的保证说，这个黄色这一边，就是所有 U 的邻居都会在这个 S 里面，它不会有在像是 V 这样的点 ，OK？ 所以这个是我刚刚没有特别指出来的地方 ，OK？ 所以如果 U 跟 V 是有相邻的，这个他们就有可能没有 common neighbor，OK？ 那如果 U 跟 V 他们是没有相邻的，那就跟这个 proof 一样。它所有的邻居都一定会在这个 S 里面，好，那我们之后就可以用反证法得到说这个是有矛盾的 ，OK？ 我们时间到，我们先休息 ，OK。 All right, okay, so let's continue, okay. So far we have considered two statements that relate the minimum degree and connectivity of a graph, okay. So first of all, we have n minus 1, okay. So if the minimum degree is n minus 1, actually the graph is complete graph. So clearly the graph is connected. And then we lower this value, okay, or this threshold. And so now it becomes n minus 1 divided by 2. And again, we can show that this time the graph may not be a complete graph. But whenever these two vertices, they are not friends, and they can have a mutual friend, okay? Now, we're going to keep lowering this threshold, okay? So previously, the threshold is m minus 1 divided by 2. I'm going to, again, minus 1, okay? So now this one is smaller than the previous threshold, okay? So we have the same question, okay? So can we guarantee that the graph must be connected, given that this minimum degree condition? Again, we can try, for example, n is 10, okay? So the minimum degree will be 3.5, which means every vertex has at least 4 neighbors. Okay. So can we guarantee that the graph must be connected if every vertex has at least 4 neighbors? So we start all the way from, say, given this n equals 10 condition, so we start from 9 neighbors. So if you have 10 vertices in a graph, and everyone has 9 neighbors, then the graph must be connected, okay? And then we consider 5 neighbors. So if everyone has 5 neighbors, then again the graph must be connected. So all the way down to 4. So now, if everyone has at least 4 neighbors, is it possible to generate a disconnected graph? Or a graph that has multiple components, but still everyone has at least 4 neighbors.有任何想法吗？OK， 所以为什么？所以两个OK， 然后这两个的大小是OK。So we can create a graph such that we have 2 components, and each component has 5 vertices. and each component is actually a complete graph. Okay. So in this case, since we have 10 vertices, so we have 2K5. Okay. So clearly this is a disconnected graph. And what is the minimum degree? So actually for this graph, every vertex has the same degree, which is 4. Okay. So this is okay. So this is a counterexample. All right. So by the way, this graph where all the vertices have the same degrees is called regular graphs. Okay. So in this case, we can say that this is a 4 regular graph. Okay. So 4 regular graph means every vertex has exactly 4 neighbors. Okay. All right, so this is a counterexample. So this means we cannot lower this threshold anymore. So the previous threshold, this one, okay? Really, this one is the smallest possible. You cannot find a smaller value for the minimum degree and still guarantee the connectivity of the graph. Okay. Right, 有任何问题吗？关于现在的到目前为止。All right, so next we're going to, again, consider some properties or problems about degrees. But this time, you need to design algorithms, okay? So let me first give you some examples of the problem, okay? So the input for the following problem is a degree sequence. So you get a sequence of degrees, okay? So for example, like 3, 3, 2, 2, 1, 1, okay? So you get some numbers as degrees, okay? And the output is, well, basically, in this problem, you need to find a graph that matches this degree sequence, okay? Okay, so by this I mean, since we have 6 numbers in our input, so we have 6 degrees, which means in our graph, we have exactly 6 neighbors, okay? And in these 6 neighbors, 2 of them have exactly 3 neighbors, and 2 of them have exactly 2 neighbors, and 2 of them have exactly 1 neighbor, okay? So otherwise, so sometimes it is impossible to find a graph that matches the input. So if so, you just output no, okay? Right, okay. So do you think it is possible to find a graph whose degrees match this input? So perhaps let's try some simpler questions or simpler input. Let's try, 1, 2, 3, okay? So is it possible to have a graph whose degrees are 1, 2, and 3. So I think it's easy to see that it is impossible, okay? So why? Because we have 3 degrees, which means we have 3 vertices. And since we have 3 vertices, the maximum possible degree is 2, okay? So we cannot have a degree of 3 in a graph that only has 3 vertices, okay? Recall that we do not have multiple edges or parallel edges, okay, between 2 vertices. So given an m vertex graph, the highest possible degree is m minus 1, okay? So this one, well, this one is impossible, okay? Now how about this one? So now we have 4 vertices, okay? And the maximum degree for a graph that has 4 vertices will be 3, okay? So 3 is possible, all right? So can we find a graph that matches this degree sequence? Yes.
Can you upload the presentation to Moodle?
Yeah, after course. And actually, I'm recording the course. So again, if you have taken my courses before, you can find my videos on YouTube. Just search TWKU 123. Okay? So the same channel. Right, okay, so back to the question. Okay. Yeah. Right, okay, so earlier we mentioned that the total degree must be an even number. Okay? So in this case, the total degree is an odd number, which means we cannot have a graph that matches this degree sequence. Okay? Now, how about this one? So 4 vertices, and vertex degree highest vertex degree is 3, and total degree is an even number. Yeah. Why?
Because if a vertex has only 1 degree,
Mm-hmm.
it means it only connect to one vertex.
Right, right.
And the other 3 vertices have 3 degrees.
Right.
Which means they all have to connect to each other.
Uh-huh. Uh-huh.
So the other can be one degree of 1.
Right, right, right. Okay, so I think to see the argument, we need to draw a graph, okay? So since we have 3 vertices of degree 3, so let's say this one has degree 3, this one has degree 3, and this one has degree 3, okay? So, well, since they have 3 neighbors, so for the top left vertex, it must be adjacent to the remaining 3 vertices. And again, for the top right vertex, it must be adjacent to the remaining 3 vertices. And for the bottom left vertex, it must be, again, adjacent to all the other 3 vertices. So you can see that for the remaining, the bottom right vertex, it must have a degree of 3, okay? So we cannot have this type of degree sequence, okay? So again, this one is impossible, okay? Now let's consider this one, okay? The previous one. So we have 6 vertices. So how So is it possible to create a graph such that you have two vertices that have 3 neighbors, and you have 2 vertices that have 2 neighbors, and for the remaining 2 vertices, they have exactly 1 neighbor? Yeah. Oh, so the graph can be connected or disconnected. Okay. So later, perhaps like next week, we're going to add more constraint such that the graph must be connected. Okay. But for this moment, we're going to just take any graph. So it can be connected or disconnected. So do you want to have a solution? OK. 所以想要怎么画吗？ So let me assign some labels. Okay, so we have A, B, C, D, E, F. All right. Okay. D, F. Okay. D, E. E, F. Okay, so let's check. Okay. So for A and B, their degrees are 1. Okay. And for C and F, their degrees are 2. And for E and D, their degrees are 3. Right. Perfect. Okay, so for this input, we can have some graph that matches the degree sequence. Okay. Now, before I give you more ideas behind this problem, I want to first give you the definition for the problem. Okay. So actually, we have a name for this kind of degree sequence where you can find a graph that matches it. Okay. So we call this graph, or we call this degree sequence graphical. Okay. So a degree sequence is graphical if there's a graph. I'll just write that matches the degree sequence. Okay. So the problem is really, so given a degree sequence, call it D, okay, determine whether D is graphical or not. Okay. And also if D is graphical, I'll put a graph that matches D. Right. So I think here the keyword is graphical. So if you want to Google some of the additional information about this problem, just Google graphical degree sequence. Okay, so now we need like a systematic way to determine whether the input is graphical or not. Okay. So for this degree sequence, do you have any general idea to get this graph? 有吗？刚刚在还是就是这样乱踹这样子 ？OK。What?
Is the one you said, but the first two are the one you just listed.
Yeah, there are some simple checks like the total degree cannot be odd, and the maximum degree cannot be greater than n minus 1.
The sum cannot exceed the combination of the. For example, in this case, it's C goes to Earth.
You mean?
Cannot exceed the maximum. For example, the one why 3331 is not acceptable is because that 3 and 3 already equals the C 4取2, which is 6, which means yeah. For example, if it takes 33111 and it's fine because you can draw it, but 3311. If you take 33, that means you have 6.
Right. So is it your idea that the total degree cannot be greater than n choose 2?
Yes, it is.
But I think for this one, well, so for choose 2 is 6, right? But so this means the total degree is at most 12. But for this one, the total degree is just 10. So it is possible to have a graph that has 4 vertices with a total degree of 10. That's possible, okay? But you're right. You can use this as a simple check to see whether it is graphical or not. Right? But even if the total degree is less than 2 times for n choose 2, it is still possible that the degree sequence is not graphical. Right. So I want to stress that at this moment we have some simple checks, right? Like the total degree is odd, or the maximum degree is too large, or the total degree is too large. Yes, we can use these simple checks to filter out some degree sequences that are not graphical, okay? But even if the degree sequence you have like passes all these simple checks, still it is possible that it is not graphical, okay? Yep.
I guess maybe the sequence, if you divide the sequence into lots of graphs, one graph the degree in that graph have to be a pair, like 就是如果那个图就是你把这几个点变成一个图，然后这个它的那个degree 可能要一样，就是要一样，就是都要有各自匹配，就是各自一样的 degree 才可以做成图。就是如果像这个，就是因为它是3个 degree， 然后你就必须要用4个点去包它，可是它没有它的，它33有一对，就是它没有，它最后一个数字是太小。就是比如说33、2可以，33、1可以。
所以我猜你应该是想要针对它去设计一个简单的 check 嘛？第一个，我猜你的 idea 是你不太可能说有很多 vertex 它都有很大的 degree， 但是一个很小。某种程度是这样。那但另外一个我要说的是，有很多 degree sequence 它不是这样的形式，就是很多 degree 很大，但是1、2个很小，也有可能不是这样的状况。那在那个状况，可能你刚刚的 idea 就没有办法派上用场。对，所以 我们需要其他的 idea？
就是degree 感觉比较相对，就比如说3321，然后我用ABC 珠列图来表示的话，那如果我 A 跟其他的 node 要连在一起的话，是代表说我 A 这个 degree， 如果我 A 消耗一个 degree， 那我其他的 node 也要相对的也要消耗一个 degree。
没错。
所以说我可以设计一个有点像法的感觉。
OK。
就比如说我 A 有3的话，那我要把 A 的 degree 降成0，那我就要把从其他 node 就是挑选他们，然后各自把他们的那个 degree 减掉1，然后从减到一直减到0，然后最后就可以创造这个 graph。
Right. So there are a few steps, okay? So the first step is that you mentioned that if we want to have a graph that matches the degree sequence, and first we can have the associated vertices, okay? So we just create n vertices. Okay, so call them V1, V2, V3. So let's just consider this 3, 3, 2, 2, 1, 1 example. Okay. So we know that from the length of the degree sequence, we know that we have 6 vertices, okay? V1 up to V6. And we also know that we have like the target degree or the number of edges that we need to add to these vertices, okay? So these numbers are like the target, okay? So we want to add 3 edges to V1, and we want to add 3 edges to V2, and so on, okay? So you mentioned a very important idea is that for V1, we have to add 3 edges, okay? Suppose we add an edge between V1 and V3. So this has the effect that we reduce this target to 2, and we reduce the target of V3 to 1, because we just add 1 degree to these 2 vertices. Right. So now the real question is, so suppose I want to fulfill this target 3. Okay? So I want to add 3 edges to V1. Now the question is, which 3 neighbors or which 3 vertices should I add edges between V1 and them? OK， 所以刚刚那个同学说的是，你就先产生这些点嘛，然后这些点，你都有一个目标的 degree，OK， 比如说 V1 的就是3 ，V2 就是3，以此类推。那我们要做的事情就是你要加 edge， 那你加 edge 的效果就是，譬如说你加一个 edge， 比如说介于 V1 到 V6 好了，那就代表，你接下来 V1 你要再加的 degree 就只剩2。然后 V6 你要再加的 degree 事实上就变0，就代表你已经满足 V6。如果我们刚刚是连 V1 跟 V6 的话 ，OK。所以我刚刚说，如果你的演算法的框架是这样的话，你要问的问题就是，当我选了 V1， 我要满足这个3个 degree 之后，我应该要选哪3个 vertex 跟它配对 ，OK。所以换句话说，我要找3个 neighbor 给 V1 就对了。当然，我们有其他5个选择 ，V2 到 V6，V2 到 V6 我要选哪3个当做 V1 的 neighbor， 所以这是我们现在要问的问题 ，OK？ 所以要选哪3个？最大的3个 ，OK？So let's try，OK？ So the first step is to create n vertices. And the second step is just pick a vertex. Vi, okay? So in our example, we first pick V1, okay? Okay, and let's let D be VI's target degree. So in our example, if we pick V1, then 3 will be the target degree. So D is 3. Okay. So according to his suggestion, we're going to pick 3 other vertices that have the highest target degrees. Okay, and then we just add edges between VI and these vertices that are picked in step 3. So let's call them U1 up to UD. Okay. Okay. All right, so let's try to apply this algorithm to this example, right? Okay, so before I even begin this algorithm, I want to first focus on the step 2, okay? So in step 2, we need to first pick a vertex. So which vertex? Do you have any specific idea on how to choose this vertex? Or anyone works? 所以我们刚刚 V1 我是随便选的，我就随便选一个离我最近的 ，OK？ 那我们在选的时候有没有要特别选谁这样子 ？OK， so we can choose anyone that you like, okay? So I'm going to pick an arbitrary or pick any vertex, okay? And by the way, after we finish step 4, we need to repeat this process, okay? So step 5 is repeat, okay? So repeat until we have the correct graph or find out that it is impossible. V1, V2. Okay. Okay, so step 1, let's pick V1. So the target degree for V1 is 3. And according to our idea, we're going to pick the 3 vertices that have the largest target degrees, which are V2 and V3 and V4, okay? Okay. So now this becomes 0, 2, 1, and 1. Okay. All right, so this is like we finish a round, then we need to start the second round. Again, we're going to pick a vertex, any vertex you like, okay? So which one? I'll let you choose. V2, all right, okay, so let's choose V2, okay? So we choose V2. And since the degree is, the target degree is 2, right? So we need to find 2 neighbors for V2, okay? Okay. And then, again, this finishes like the second round, okay? And we're not finished yet, okay? Because we still have some non-zero target degrees. So, okay, let's pick V5, okay? So since the target degree is 1, which means we need to find one neighbor for V5. And in this case, we can only choose V6, okay? So after this round, you can see that all the target degrees are 0, okay? So this means we do not need to add any more edges to the graph. And yes, so this graph matches the input degree sequence. So it is 3, 3, 2, 2, 1, 1, okay? So, so is this algorithm correct?
For unconnected purpose, yes, that's correct. If you are aiming for finding unconnected graphs, then it's correct, I think.
Yeah, we are okay with disconnected graph. Yeah, so any idea why this algorithm is correct? So there are some design choices in this framework. So first of all, in the second step, okay, you need to pick a vertex. So here for this step, what we wrote here is that we can pick any vertex you like, okay? But then in step 3, when we have to pick D vertices, we cannot choose, at least from this statement here, we did not choose any arbitrary D vertices. We pick the one that has the highest target degrees, okay? So can we change the design here? For example, can we change this highest to like the lowest?
Is this algorithm considering the constraint information before? For example, like the maximum number cannot exceed the vertex number. For example,
Not really. Okay.
So if you add the constraint, add the constraint before the step 1, for example.
So you mean that if we have the simple checks first, and then run this algorithm,
It should be fine. Like start from any other like random vertices.
No. So actually, for the third step, if we change this to the lowest, okay? So let's see. Okay. So we're going to apply the modified algorithm where in the third step, we're going to choose the one that has the smallest target degrees. And again, you can apply the simple checks like the total degree, the maximum degree, or if the total degree is too large, or if the total degree is odd. And you can see that this degree sequence, it passes all the simple checks, right? The total degree is even, okay? And the maximum degree 3, well, it is not too large. And the total degree, it certainly is less than twice 6 choose 2. Okay, so it passes all the previous simple checks, and then we run the algorithm. Okay, so let's see what happens. So again, we choose V1. Okay, in our second step, so we need to find V1 3 neighbors. Okay, but this time we're going to pick the one that has the smallest target degrees. So okay. Now, after we add these 3 edges, the target degrees becomes this. Okay. Okay. So this finishes the first round. In the second round, again, let's pick V2. Okay. Now you see there's a problem, okay? So when we pick V2, because the target degree is 3, which means we have to add 3 neighbors. But now we can only choose V3 and V4, okay? Because all the other target degrees are 0, so we cannot add them as neighbors for V2. So at this moment you can see, okay, according to this algorithm, we cannot find a graph that matches the degree sequence, okay, according to this algorithm. But clearly, the degree sequence is graphical, which means the algorithm is wrong, okay? So this algorithm cannot find a graph that matches the input. Therefore, it is wrong, okay? Okay. Because we know that actually there are some graphs that matches the input degree sequence, okay? So what happens here is that we have an algorithm, and we apply the algorithm to some degree sequence, and the algorithm tells us that no, it is impossible. However, it is possible because the degree sequence is graphical, okay? Now, can the first algorithm have the same problem? Is it possible that the first algorithm tells you that it is impossible? However, the degree sequence is graphical. Okay. So in other words, we need to prove that the algorithm is correct. I'm going to leave the proof to the next week, but we can try more examples. Okay. Okay. Let's apply the previous examples. Okay. So let's try this one. Okay. Okay. So the target degrees are 3, 3, 3, and 1. Okay. And well, let's use the first algorithm. That is, whenever we need to pick D versus, we need to pick some neighbors. Okay. We always pick the one that have the largest target degrees. Okay. Yeah. So. Say let's pick V1, so the target degree is 3, which means we need to find 3 neighbors. Now after we add these 3 edges, the degree sequence becomes 0, 2, 2, 0. Okay. So actually, from this moment, you can tell that this cannot be graphical. Okay, but let's keep applying the algorithm. So let's choose V2. So for V2, the target degree is 2, which means we need to find 2 neighbors. But for this input, we can only choose V3 because it is the only one vertex with a positive target degree. Okay, so this algorithm will return no, this degree sequence is not graphical. Okay. Okay, so more examples. This time let's try 1, 1, 2, 3. Okay. Okay. Again, let's pick V1. Okay. So we need to find one neighbor. So we're going to pick V4 because it has the largest target degree. Okay. And then let's pick V2. So this, in this case, we can pick either V3A or V2, okay, because they all have the largest target degrees, okay. So we can break ties arbitrarily, okay. Suppose we add V3, okay. Okay. Next, let's pick V3, okay? So the target degree is 1, so we need to find one neighbor, okay? Okay, so this time we consider the degree sequence is 0, 0, 0, and 1, okay? So when we pick V4, you can see that we need to add one neighbor, but it is impossible because all the other 3 vertices, their target degrees are 0, okay? So not graphical. Or the algorithm returns okay. So yeah, so in the next week we're going to discuss the correctness of the algorithm, okay? So it turns out that the algorithm is correct, okay? So when the algorithm returns not graphical, really the degree sequence is not graphical. All right. So see you next week.